Okay, this is chapter 27, example 5, and what we have here is a circuit we need to design. It inputs two 10-bit unsigned binary values, and what I need to do is dividing those values by 2 until the sum of those two values is 255 or less. 255 or less is 8 bits. So we're inputting two 10-bit values, and we essentially need it to fit into an 8-bit word, Howard. And the way we're going to do it is divide by 2. You can already see that it's going to be some type of shift register problem, but let's do the first thing first here is draw the circuit diagram, high level black box diagram. It's going to have an 8-bit input or 8-bit output, and that's going to be a sum, and it's going to have a clock on the input. It's going to have a button. So the next thing we need to do in here is kind of devise a way to do this. Now this could be done not too easily using one shift register, but the problem is much easier using two shift register. For this problem, I am shifting values to the right. I'm shifting both values to the right. So I'm going to put down two shift registers. Now these shift registers certainly have select inputs, as we've always been using them, but you can see hopefully that the select values are going to be the same for both of these shift registers. We're going to put those together and list these as a 2-bit bundle there. Also, these shift registers have data inputs. The data is going to be coming from the outside world. It's 10 bits. So the next thing we need to do here is take these outputs. We need to see if the sum is 255 or less. And so first thing we need to do is sum them up. We only have one way to do a sum. So the last thing I need to do in this circuit is I need to make the output persistent. Now the only way to make it persistent is to use a register. Okay, so the input, so we have to deal with this. It has a data input. We're only, and this is a 10-bit output, and we're only going to use the bottom 8 bits. And by the time we load this register, we're only going to be using the bottom 8 bits. So we'll say remove. And so this is a clocked circuit also. And what we need to do here, we probably need some load control on this one. We don't need to clear the circuit because the only thing we're going to do to this circuit is load it eventually. And we're going to load it when the sum is 255 or less. And once again, we had to shift it. We're shifting at the same time, so we got shift registers. We're looking at the sum, so we needed an adder. And then we need the output to be persistent, which is a register. So in between, we just matched up the data values with whatever we needed to do. So the last box we need in here is some way to control this circuit, and so we'll just list these. There's a load, and here's a select. It's a 2-bit value, and this is clocked, of course. And the status, the only other status we have in this one is, of course, a button, and we need one more thing. Now the issue here is we're adding these values. It needs to be less than 255, which means that the top 2 bits need to be 0 of this 10-bit value. Additionally, the carryout has to be 0 also. So what we have here is 3 values that need to be 0, and we'll call these, we'll call this right here 2 MSBs. This is obviously the carryout here. This gives us the, we'll call this, give it a good name. And that becomes a status input, LT255. That's the status input we're looking for in this particular problem. And at this point, I think we're ready to generate the state diagram. Once again, if we forgot something, we will come back and put it in later. Start of this thing off, it is, like many problems here, is waiting for a button press. When I get a button press, I am going to, what am I going to do on this thing? Since I know I need to do this on the other part, I will say select equals 0, 0. So we need to fill this in. Button's not being pressed. What we're doing here is nothing. This is kind of a don't care in this case, but when someone does press a button, what we have here is we need to load both of these shift registers, and we're going to load that with a load, and we'll call this the divide state. Okay, and that looks good. I'm kind of worried about this other value here. Usually I'll come do this at the end, but in this state, output's persistent, so I want to make sure that I do not load that output register. And it looks good here. So I'm going to stay in this state so long as LT255 is not on. When it does turn on, indicating the value is less 255 or less. Actually, it should be LT256, huh? Well, whatever. 256. Once we lessen that value, we're going to go back to the wait state. So while I don't have that value, I'm not loading the circuit. When I do get that value, that sum less than 256, I am going to load that register. While I am in this state, I can treat this select value as a more output, and the thing I'm going to do here is shift it right 1, 0. Load is handled and select is handled in both of these states, which are the two control outputs of the state machine. One thing that you'll see here, and when I do get that value less than 256, it will still shift the output, but that's okay. What I'm more interested in is loading the sum result into that register, which happens there. By that time, I've shifted these shift registers again, but I don't really care anymore. The only thing I need to do is keep that output persistent, and I've done that as is. So lastly, in the circuit here, I need to say how it's controlled. And these are control inputs. The registers are load, handled by the state machine. Additionally, the control inputs of the shift registers are handled by the state machine also. So this is going to be... This problem has a slight error in it. The USRs have a D-bin input, which is the bit it inserts on the left side when it shifts right. That should be grounded. And with that, I am going to call it done.